Lathes perform many kinds of machining operations, facing, turning, grooving, and chasing both inside and outside diameters. They can also be used to drill, to ream, and to tap. In all of these operations, the lathe removes material from a workpiece by rotating the workpiece against a cutting tool. Performing each of these operations requires special procedures which must be followed for the work to be produced properly and safely. On this program, we will look at the two most basic operations performed on a lathe, facing and turning. In facing, the cutting tool creates a flat, square surface by cutting across the width of the workpiece. Turning is an operation in which the cutting tool removes material as it moves along the length of the workpiece. This program discusses two kinds of turning operations: cylindrical turning, in which the cutting tool is fed across the length of the workpiece to turn an outside diameter, and cylindrical boring, in which the cutting tool is fed into the workpiece to turn an inside diameter. All operations in this lesson will be performed using a single kind of steel, plain carbon steel, and just one cutting tool, a high-speed steel bit. You should not attempt these operations with any other material or with any other tools unless you are qualified to do so. Personal injury and damage to the lathe may result. To perform turning and facing operations on a lathe safely and efficiently, you must know how to mount the workpiece, how to select the cutting tool and operating speeds, and how to operate the lathe properly. Let's begin with an overview of the lathe and how it works. It has three major parts: the headstock, the carriage, and the tailstock. Workpieces being machined in a lathe are either held in place by the headstock alone, or they are held between the headstock and the tailstock. The tailstock can be moved to accommodate the workpiece, then clamped firmly into position. A motor in the headstock rotates the workpiece when the lathe is turned on. Between the headstock and the tailstock is the carriage. It allows precision adjustment of the cutting tool. For setup, the carriage is moved back and forth with a hand wheel, but in operation it is power-fed by the same motor that operates the headstock. Now let's look at each of these in more detail. The principal parts of the headstock are the spindle, which turns the workpiece, and the motor and its gearing, which drive the spindle and other parts of the lathe. The spindle is a hollow tube mounted on anti-friction bearings and extending straight through the headstock so long workpieces can be accommodated. All spindle noses are tapered on the inside to align the mounting which holds the workpiece being machined. The operating speed of the spindle is indicated on the machine in revolutions per minute, RPM. On some lathes, the speed is set with a variable speed selector dial. On others, the speed is controlled by a series of stepped pulleys, by a gearbox, or by both pulleys and a gearbox. Most spindles can also be shifted into neutrals, so mountings and workpieces can be free-wheeled. Many can be braked, as well as operated in reverse, and most can be locked into position. The motor driving the spindle and the workpiece also controls the carriage. Power is transmitted through a separate gear train to a feed control rod, which moves the carriage and the cutting tool across the workpiece. The rate at which the tool moves is called the feed rate and is measured in inches per revolution of the spindle, or IPR. This feed rate is set with a series of levers according to a chart affixed to the front of the headstock. The same gearing also operates the lead screw, which controls the movement of the carriage when the lathe is used to cut or chase threads. The principal parts of the carriage are the apron and saddle, the top and bottom slides, and the tool holder. The carriage moves back and forth across precision ground bedways or ways between the headstock and tailstock. Any damage to the ways will affect the quality of the work produced, so it's important to keep them very clean and free of any nicks or burrs. Never lay a tool across them, and never move the carriage unless you've checked to make sure the ways are clear and clean. And make sure the surfaces are lightly oiled at all times. The saddle spans the ways and supports two slides, the bottom slide and the top slide. The tool post, tool holder, and the tool all fit into a T-slot in the top slide. Adjustments of the tool for most lathe operations are made by moving the slides with their hand wheels. The micrometer dials which measure this movement are not the same on all lathes. One lathe may have direct read dials, while another may have diameter reduction dials. Some dials indicate how far the slides are actually moved, so the cut taken by a tool is twice the amount set on the dial, since the tool cuts into both sides of the workpiece. For example, moving this kind of dial 50 thousandths of an inch removes 100 thousandths of an inch of the workpiece, 50 thousandths from both sides as the workpiece rotates. Another kind of dial moves the slides half the amount indicated on the dial, so the diameter of the workpiece is reduced by the amount set on the dial. For example, moving this kind of dial 50 thousandths of an inch removes 50 thousandths of an inch from the workpiece, 25 thousandths from both sides as the workpiece rotates. If you are not certain which kind of dials are on your lathe, you should measure how far the slides actually move and compare that distance to how far the micrometer dial has moved. Like the headstock, the tailstock also has a hollow tapered spindle. In addition to holding a workpiece on a center, the tailstock spindle can also hold drill chucks, drills, reamers, and other tools. The entire tailstock body is moved back and forth across the ways manually during setup, then bolted into position. Make sure the ways are clear and clean before moving the tailstock. Movement of the spindle nose is controlled by the hand wheel at the end of the tailstock. After the proper adjustments are made, the spindle is clamped into position with the binder handle on the tailstock body. Preparing for an operation on a lathe is always a two-part process. The first part is to mount the work securely in the proper position. Mounting the workpiece properly is critical for accurate lathing as well as for safe operation. Mounting can be done in many ways, but the most common are mounting in chucks in the headstock spindle, mounting between centers in the headstock and tailstock spindles, and mounting on faceplates, which in turn are mounted on the headstock spindle. When mounting a workpiece requires the removal or the addition of a chuck or faceplate, the lathe must be locked out. A lockout should be performed whenever doing setup work at the headstock that is not a part of regular routine operation of the lathe. Now, before you actually mount anything in the spindle, make sure all mating surfaces are clean, as well as free of any nicks or burrs. The spindle nose should be wiped out with a clean rag on a stick. After that, carefully feel the internal taper to make sure no chips or other material have been embedded in the internal surface of the spindle. Spindles may be damaged if they are not carefully cleaned, and mounting anything in an unclean spindle may cause it to wobble as it turns. Working with chucks can present three hazards. The first arises when mounting chucks in the headstock spindle or taking them out again. Many chucks are very heavy, and attempting to hold them at the proper angle and height to attach them to the spindle will cause muscle strain in the arms, shoulders, and back. Chucks that cannot be lifted easily should be placed and held in position with an overhead hoist, with the help of another person, or by using a properly sized wooden support placed on the ways. The second hazard is chuck keys. Keys left in a chuck will fly out at high speed when the lathe is turned on. Many keys are now self-ejecting, so they cannot be left in the chuck, but it's still a good rule to never let go of the key until it has been returned to its proper place. The third hazard is improper use. Chucks rely on clamping force to hold a workpiece in place, but when a lathe is in operation, centrifugal force can reduce the clamping power by as much as 2/3. Improperly chucked workpieces can fly out of the lathe, causing serious injury, damage to the workpiece, and damage to the lathe. Proper chucking is essential for safe operation, so make sure you know the correct procedures for mounting work in the chuck you are using. Three kinds of chucks are common: the 3-jaw universal chuck, the 4-jaw independent chuck, and the collet chuck. Both kinds of jawed chucks are tightened with a key, while collet chucks squeeze the collet around the workpiece. In a three-jaw universal chuck, all three jaws are moved by a single pinion gear turned by the key. As the key turns, the jaws move simultaneously through slides machined into the body of the chuck and clamp the work into place. For many applications, a three-jaw chuck will mount the work with sufficient accuracy. For more accurate work, however, some three-jaw chucks include 4 additional screws, which can adjust the position of all 3 jaws simultaneously. A dial indicator is placed into position, either mounted in the tool holder or placed across the ways. As the chuck turns, the high and low points on the workpiece are indicated. The adjustment screws are moved until the workpiece is centered, usually to within 1/1000th of an inch. A 4-jaw independent chuck is often used when more accuracy is required routinely. Each jaw of the chuck is open just enough to permit the workpiece to be inserted. Concentric circles scribed in the face of the chuck are used to determine the approximate center. Then each jaw is clamped into place, but only lightly. As with a 3-jaw chuck, a dial indicator should be used. Jaws on opposite sides of the chuck are adjusted in pairs until the workpiece is centered. Collet chucks and collets are also commonly used. Collets are made in specific sizes and should not be used to hold workpieces larger or smaller than they are designed for. The size is marked on the collet. Collets that are too small or too large will be unable to grip the workpiece properly, so the machining will not be accurate, and the collet may be damaged as well. You should measure a workpiece to make sure it fits the collet. As the chuck is tightened, an adapter compresses the collet and the workpiece is gripped firmly. When a workpiece is not chucked, it is often held between centers. These are hardened steel pins inserted into the spindles of the headstock and tailstock. However, before a workpiece can be mounted between centers, it must be center drilled. This means the workpiece must have holes drilled at the precise center of each end of the workpiece. A special center drill is used for this purpose. Accurate center holes may be drilled by mounting a workpiece in a chuck and centering it with a dial indicator. Next, mount the center drill in the spindle of the tailstock and adjust the tailstock so the bit is close to the end of the workpiece. Turn on the lathe and advance the drill into the workpiece by turning the tailstock handle. Reverse the workpiece to center drill the opposite end. Once the workpiece is center drilled, the centers can be inserted into the spindles. If the center is smaller than the spindle, an adapter is used. When inserting centers or adapters, remember to clean the spindle nose carefully, because any irregularity will force an inserted center out of line. Both the center and the workpiece will wobble, and the workpiece will not be accurately machined. After inserting the centers, you should check the lathe for proper alignment of the headstock and tailstock. Checking the alignment is often done by moving the tailstock across the ways until the centers in both headstock and tailstock are close to each other but not touching. Anything less than perfect alignment of the center tips indicates the centers are not properly installed in the spindle or that the lathe requires precision alignment by a qualified person. If the lathe is properly aligned, it is ready for a workpiece to be mounted. When workpieces are mounted between centers, drive plates and dogs are used to transmit the power of the lathe to the workpiece. Drive plates are usually cam-locked, keyed, or threaded around the headstock center. The dog is slipped around the workpiece and the workpiece is placed between the centers. The dog's bent tail is inserted into one of the slots in the drive plate. Make sure the dog is the proper size and that its tail fits loosely into the slot. Dogs that are too large may bind, causing the center to unseat and the work to turn eccentrically. Once the workpiece is mounted, the dog's set screws are firmly tightened. When workpieces with unusual shapes cannot be easily held in chucks or between centers, they can be bolted or clamped into position on faceplates. Faceplates are like drive plates but are generally larger and have several holes and slots for mounting workpieces. Very often, work mounted on a faceplate must be counterweighted to even out unbalanced centrifugal forces. Properly mounting work on a faceplate requires a high level of skill and should not be attempted by an unqualified person. When long workpieces require additional support for proper machining, steady rests or follower rests are used to prevent the work from springing away from the cutting tool. Turning, facing, and most other lathe operations require single-point cutting tools. These are usually made from high-speed steel or cemented carbides, although sometimes carbon tool steels and cast alloy steels are used. Many modern single-point cutting tools are made from ceramics and cermets. Most tools will cut most materials, but the speed at which materials should be cut will vary widely depending upon which kind of tool is chosen for the application. Using the wrong tool or the wrong speed may damage the tool or the workpiece and could cause personal injury. Tables provided by material suppliers and published in machinist handbooks will provide useful starting points when determining how fast to cut a workpiece with a particular tool. The charts normally include an indication of the material by its common name, by its number, and often by its hardness rating. All of this information may not be available for your workpiece, so if in doubt, ask someone more familiar with the materials used in your facility. Don't forget to make sure you're using the proper tool. Most repair and maintenance work can be done with tools made of high-speed steel, but if the job is a big one, carbide tooling may be a better choice, since it can be used at faster speeds and will get the work done more quickly. Notice that the tables specify the cutting speeds in surface feet per minute. The speed of the lathe, however, is measured in revolutions per minute. To make a quick conversion that will fit most situations, multiply the feet per minute times 4 and divide by the diameter of the material. For example, an 1.5-inch bar of plain carbon steel with a hardness rating of 250 should be cut at 70 feet per minute with a high-speed steel tool. 70 times 4 equals 280. 280 divided by 1.5, the diameter of the steel bar, equals 186. The lathe should be operated at 186 RPM, or as close to that speed as possible. You should remember that a larger diameter shaft requires the speed of the lathe to be reduced. For example, a 3-inch bar of plain carbon steel would be cut at about 93 RPM. 280 divided by 3. This is because at any RPM, the surface speed of the workpiece passing under the cutting tool will increase when the diameter of the workpiece increases. To maintain the same feet per minute cutting rate, the RPM must be decreased. Cutting should be done as close as possible to the recommended cutting speeds. When in doubt, cut more slowly, because cuts made at excessive speed will dramatically reduce the life of the cutting tool. Using a high-speed steel tool at 10% above recommended speed may cut its life in half. The tool may even have to be resharpened or replaced before completing the job. Two other factors are also important when determining the speed at which the workpiece should be machined: the feed rate and the depth of the cut. The feed rate is the rate at which the tool is fed across the workpiece, typically about 12/1000th of an inch per revolution. Gearboxes can usually adjust the feed rate from a little more than 1/1000th of an inch to about 1/10th of an inch per revolution. The depth of cut is how deeply the tool cuts into the workpiece. A typical cut is 1/8 of an inch. Most tables of cutting speeds will indicate the feed and depth factors upon which they are based. Generally, as either feed rate or depth of cut rise, cutting speed should be reduced, and as feed rate and depth of cut decline, the cutting speed can be increased. Once the lathe is properly aligned and the work is properly mounted, and once the proper cutting tool, speed, and feed have been selected, the operation can begin. In all lathing operations, the tool bit should extend just far enough to expose the cutting edge, and the tool holder should extend no farther than necessary. The nose of the cutting tool should be on center, that is, at the same height as the headstock and tailstock centers. This maintains the rigidity of the setup and enhances the finish of the workpiece. Make sure all guards are in place before the lathe is switched on. Facing is a finishing operation usually done to a precise length. The proper procedure is to machine just enough stock from one end of the workpiece to clean up the surface. After facing one end, the workpiece is removed, then the remaining stock removed from the opposite end. To make either facing cut, position the cutting tool at the face for the desired depth of cut. Then turn on the lathe and advance the tool across the width of the workpiece. If the second cut requires the removal of large amounts of stock, it may be faster to make a series of deep, longitudinal cuts into the workpiece from the outside diameter. This is called step facing. Turning an outside diameter should always be a four-step process: trial cut, rough cut, trial cut, and finish cut. The first trial cut and the rough cut should reduce the workpiece to a diameter about 50 thousandths of an inch larger than the finished size. For example, if the finished size of a shaft is to be 1 inch in diameter, the rough cut should reduce its diameter to about 1 inch and 50 thousandths, 1.05 inches. The first step is to take a half-inch long trial cut into the work. Make absolutely sure this cut leaves the work more than 50 thousandths of an inch larger than the finished size. Measure the precise diameter of the trial cut with a micrometer. Then set the bottom slide micrometer dial to cut the difference between the trial cut and the desired diameter of the rough cut. For example, if the trial cut was measured at 1 inch and 60 thousandths, 1.06, the bottom slide should be set to remove an additional 10 thousandths of an inch. Make sure you know how the dials on your lathe operate. After the rough cut is made, measure it to be sure it's correct. The next step is to take another half-inch long trial cut to bring the workpiece very close to its finished size. Typically, the second trial cut should reduce the workpiece to about 25 thousandths of an inch larger than the diameter of the finished piece. As before, the trial cut should be measured with a micrometer. Be sure you measure carefully, because the accuracy of your measurements will determine the final size of the workpiece. If the second trial cut is not the intended size, something is wrong. The tool may be dull, you may have made your measurements wrong, or you may be setting the slides incorrectly. If the diameter of the second trial cut is correct, reset the bottom slide micrometer to take the final 25 thousandths of an inch from the diameter of the workpiece and make the final cut down the length of the shaft. Cutting an inside diameter is a very similar process and follows the same four steps: trial cut, rough cut, trial cut, and finish cut. Measurements are usually made with inside calipers, but the real difference is that the rough cut may have to be taken in several steps. That's because the shanks of boring tools often deflect when deep rough cuts must be made. If you do have to make multiple rough cuts, be sure to precede each rough cut with its own half-inch long trial cut. This should assure that each rough cut will always remain well above the depth required to make the final cut. No matter what kind of operation you are performing, remember to keep chips from building up around the work area. Make sure the lathe has stopped rotating before removing chips, and use a hooked handle or a brush to remove them, never your hand. Chips can be hot as well as razor sharp. The operations we've demonstrated can be performed in other ways, but doing so requires additional training. Unless you get that training, perform your facing and turning operations exactly as we've demonstrated. And remember, if you will be machining any other material or using any other tool, Get the proper training first.